I think this is some of the most detailed and in-depth testing of VTX output power that's ever been done in the FPV community. And I want to take a moment to give you a summary of the results up front. 1600 milliwatts is about 1000 milliwatts. 1200 milliwatts is more like 200 to 250 milliwatts. 25 milliwatts is more like 200 milliwatts, and 200 milliwatts could be as much as 600 milliwatts. And all of that's absolutely true unless you use an antenna. So now that we've covered all that, let's get into the video. In this video, I'm going to be looking at the output power of different VTXs, but not just analog VTXs. For the first time, we're going to be accurately measuring the output power of a whole range of different digital VTXs as well, from DJI, WalkSnail, and HDZero. And I was totally shocked at the results, and I cannot wait to share them with you. In this video, I'm going to be taking you through the test setup, a bit of the theory behind how we measure VTX output power, and why it's really hard to measure digital VTX output power, much more difficult than for analog. And then we're going to be looking at the test results and seeing how all these different VTXs stack up against each other in terms of their output power. It's a lot to cover in one video, and this one's going to be a banger. So let's not waste any more time. Let's get right into it. All right, so let me take you through all of the test equipment I used to gather this data, starting over here with this analog RF power meter. This is a very similar device to the Immersion RC RF power meter that you may have heard of, and it's suitable for measuring the power output of analog VTXs, but it's not suitable for measuring the power output of digital VTXs for reasons that we'll come on to in a little bit. So this power meter was mainly used to check and to calibrate the rest of the test setup. The VTX on test goes here, and I've got an analog VTX set up at the moment, and it's powered from this power supply. And for all of the VTXs that I tested, I powered them all from 16 volts, apart from the 1S VTXs, which were powered from 4 volts. The VTX on test can either be connected to this RF power meter or connected through to this RF power meter that I've built specifically for this testing. In both cases, the VTX is connected through a 30 decibel attenuator. And the reason for that is that all of these meters can only measure up to around 2 milliwatts of RF power. And of course, our VTXs go a lot higher than that, up to, well, in some cases, over 1 watt. So you need to attenuate that RF power signal down to a level that is within the range that these meters can measure. And we do that using a 30 dB attenuator. That means that the readings that we see on these power meters are going to be 30 dB less than what the VTX is actually outputting. And these attenuators have a really nice flat frequency response all the way up to 6 gigahertz. So they're going to be really suitable for the testing that we want to do with our 5.8 gigahertz VTXs. Coming on to the power meter that I built specifically for this testing, it uses two ADL5902 true RMS power meters, and they can measure signals from 50 megahertz all the way to 9 gigahertz across a wide dynamic range. And these meters are a little bit special because they can measure signals no matter the frequency, the bandwidth, the modulation, the crest factor, which we'll talk about in a bit. It can measure signals regardless of their characteristics. And that makes them really excellent for comparing VTXs which have very different modulations. So analog versus digital VTXs, for example, or DJI versus HDZero. These true RMS meters provide an analog voltage that's proportional to the power of the RF signal that they receive in dBm, so they're linear in dB. And the output from these two modules go into the analog input of this Arduino, which measures that voltage very accurately and then reports it as a millivolt value on the screen. And it also calculates the total power output being measured by both of these modules, converts it to a milliwatt reading, just a quick check while you're working, and it also measures the supply voltage here. Finally, we have a small desk fan here, which keeps the VTX cool while it's operating at higher power levels, and the whole test setup is inside an air-conditioned room, which is held at a constant 25 degrees during the testing to help avoid any influence of temperature on the test results. Now that we've looked at the test equipment, I want to talk you through everything that I've learned about measuring VTX output power, as well as how VTX output power affects things like range and penetration of our video links. Okay, so the first thing to know is that there are actually two different measures of VTX output power that we need to be aware of and that regulators care about. The first is conducted output power. Now, conducted output power is the power sent to the antenna through the antenna cable by the VTX. And this is, I think, what we think of in FPV as VTX output power. It's the power actually transmitted to the antenna. The second measure of output power that we need to be aware of is EIRP, or effective isotropic radiated power. And this is how we measure the power output of a radio signal once it's left the antenna, once the VTX has transmitted it. If we take a signal that is broadcast with 1 watt of power omnidirectionally in all directions equally, then that signal has an EIRP of 1 watt. However, if we take that same signal broadcast with the same 1 watt of power, but we broadcast it in a tight beam that only covers 10% of the available angle, then that signal has an EIRP of 10 watts and an antenna gain of 10 times. So the EIRP is the conducted output power multiplied by the antenna gain. In FPV, we tend to use omnidirectional antennas on our drones. So these antennas have a low gain near 1 and may broadcast equally in all directions. And the reason for that is we want our VTX signal strength to stay the same no matter what orientation the drone is in. So here you can see the green circle. That's an isotropic radiating antenna. It radiates equally in all directions, and you can see that no matter where we are, we're getting good VTX signal. And if we flip the drone upside down or turn sideways, it doesn't change the amount of VTX signal that we're getting. If, however, we look at this 10 watt EIRP signal that's directional, we can see that if we are in the path of the beam, we get exceptionally strong signal. But if we're anywhere else, we get almost nothing. And so that's the trade-off with having high antenna gain, is you're going to get stronger signal in some directions and a much weaker signal in other directions. In general, for FPV, that's not desirable. And so we tend to focus on using omnidirectional antennas. If we're using an omnidirectional antenna with a low gain near 1, then our EIRP is going to be close to or the same as our conducted output power. Our analog VTXs are also specified by conducted output power. So that's the output power specification that we're most familiar with. But DJI and WalkSnail Avatar don't do this. And so that's something that we're going to be talking about more later in the video. So why can't we use an ordinary analog RF power meter like this Immersion RC RF power meter for measuring the power output of a digital VTX? Well, it turns out it all comes down to the crest factor of the signal. Crest factor is a measure of the maximum instantaneous power of the signal divided by its average power. If we look at this diagram, you can see that the red signal has a large crest factor because it's very spiky, it's very bursty. Its instantaneous power is very large, but its average power is very small. Whereas the blue signal has a small crest factor because its average power is much more similar to the maximum instantaneous power of the signal. Digital VTX signals have really large crest factors, and the reason for that is that the modulation schemes that they use prioritize getting the maximum bit rate out of the width of channel that they have. So they have a channel width of a certain size, and they want to get the maximum bit rate out of that channel width. And it turns out that modulation schemes with high crest factors are able to achieve higher bit rates with the same channel width, and so they're preferred for these digital systems. Analog RF power meters tend to underestimate signals with high crest factors because they can't accurately resolve these very short, sharp bursts of power, and they tend to underestimate them. My DIY power meter uses devices specifically designed to measure these types of signals accurately, and so it's able to report an accurate RMS power independent of the crest factor of the signal. Now it's time for a word on regulation, and the first of several revelations I had whilst doing this VTX power testing. In the USA, FPV VTXs transmit in the amateur radio band, and this means that you need a ham license to operate above 25 milliwatts of conducted output power unless your VTX is Part 15 certified. And the only FPV VTXs that are Part 15 certified, as far as I know, are the DJI O3 Air Unit and the original DJI FPV Air Unit, not the Vista. The Caddx Vista is not licensed. So if you have a ham license, you can transmit up to 1 watt of conducted output power and up to 4 watts of EIRP, i.e. up to 6 dB of antenna gain on top of the 1 watt of conducted output power that you're allowed. Conducted output power above 1 watt would not be compliant with FCC regulations. But, and here's the fun bit, DJI reports EIRP for its output power, which means that when you're operating the Air Unit or the Caddx Vista in 1200 milliwatt mode, you're actually way below 1 watt of conducted output power and way below the 4 watts of EIRP that you're allowed with a ham license. So if you do have a ham license, you can feel confident to operate the Air Unit or the Vista in that full 1200 milliwatt mode and know that you're not breaking any regulations as far as I'm aware. In the EU and the UK, the rules are a little bit different. In these countries, the maximum transmit power for airborne use of the 5.8 GHz band by an unlicensed device is 25 milliwatts EIRP. Licensed devices may be allowed to transmit a lot more power than this, depending on exactly what their license states. And my DJI O3 Air Unit transmits about 250 milliwatts of conducted output power in CE mode, which, when you include that with the 1.5 dB of antenna gain that the stock DJI antenna has, gives about 350 milliwatts EIRP for the O3 Air Unit in CE mode. And clearly that's a lot more than the 25 milliwatts that would be allowed for an unlicensed device. And that's one of the benefits of licensing a VTX in the way that DJI has with O3. It's quite intuitive that using more VTX power is going to give us more range and penetration on our video signal. But the relationship is non-linear. Every time we increase the VTX power by a factor of 4, we get twice the range. And the reason for that is something called the inverse square law. This diagram shows how it works really nicely. If we're some distance r from a radio source, the radio signal is spread over a certain area A. If we move to twice the distance, then that area over which that radio signal is spread increases by a factor of 4. Which means that if we wanted to have the same signal strength at 2R that we were enjoying at R, we'd have to increase the power from our VTX by a factor of 4. And if we move out to 3 times the distance, you can see that now the radio signal is spread over 9 times the area. And so if we want to get 3 times the range, we need 9 times the VTX power. And as you can see, the relationship is that the power must increase as the square of the distance that you go. What this means for our uses in FPV is if we want to continue to double the range, every time we double the range, we have to increase the power by another factor of 4. So if we move from 25 milliwatts to 100 milliwatts, we'll get twice the range. If we want twice the range again, we have to go to 400 milliwatts. And if we want twice the range again, we would have to go to 1600 milliwatts. And you can see that we're getting 8 times the range at 1600 milliwatts than we enjoyed at 25 milliwatts. But we're using 64 times the amount of power. The result of this is that often in terms of range and penetration, you're not going to see very much difference between 800 and 1000 milliwatts or 600 and 800 milliwatts. The larger differences are going to be from 25 to 200 and from 200 to 400 or 200 to 800. That brings us to the end of the theory. And if you have any questions on anything that I've covered, please leave a comment down below and I'll do my best to answer them. Now let's move on to looking at some test results and see how these different analog and digital VTXs compare in terms of output power and see how their output power varies, sometimes substantially, depending on what channel you select for your VTX. Alright, let's get into some hard data now and start by looking at a couple of analog VTXs. The way that I'm going to show the plots for all of this data is we're going to have frequency on the x-axis, and I'm also going to put a label here to show you the corresponding channel for the frequency that we're measuring. The output power is going to be conducted output power. So that's the output power that we commonly use when we're specifying VTXs in FPV. And that conducted output power is going to be displayed on a logarithmic axis. So you can see that we go from 10 milliwatts to 100 milliwatts to 1000 milliwatts. And we also have these small lines in between to show you, 100, 200, 300, 400, 500 milliwatts. The reason that we're going to display all these results on a logarithmic axis rather than a linear axis is that we can then place these arrows on the axis. Now this arrow indicates how far up the y-axis you need to move from any point to get twice the range and penetration. And we have this green arrow which shows you how far you have to move up the y-axis, again from any point, to get 1.4 times the range and penetration. So we can move these arrows around sort of in our minds and see, okay, well, the distance from that grey dot to that yellow dot is about the length of this green arrow, which means that from grey to yellow is going to be about 1.4 times the range and penetration. Whereas if we look here, well, maybe this blue dot and this grey dot are more like twice the range and penetration. So that's what the purpose of the arrows is for. The next thing to look at is how accurately these analog VTXs hit their specs in terms of output power. We'll start on the right hand side with this Caddx VTX, and we can see that at 25 milliwatts, it's putting out about 50 milliwatts of output power. So it's quite a bit above the nominal value there. But once we get up to 200, 600 and 1000 milliwatts, you can see that it's pretty much on that 200 milliwatt line, give or take. And so it's going to be pretty accurate in terms of 200 milliwatts of output power. If we come over and look at the Caddx Pro VTX, we can see that the 200 milliwatt setting is reasonably accurate, maybe a little high in the higher channel numbers. But when we get up to the 400, 800 and 1600 milliwatt power settings, the actual conducted output power is quite a bit less than what we would expect based on the nominal output of the VTX. So we can't always rely on the nominal specs of these different VTXs. We definitely have to measure them and see how the output power corresponds to the specified output power in the setting. It's interesting to note in this case that even though these two VTXs have very different maximum ratings, 1000 milliwatts and 1600 milliwatts, we don't see a big difference in their output power in the highest power mode. Let's look now at the DJI FPV Air Unit, the V1 Air Unit. Now this VTX has two antenna outputs, so we're going to need two plots, one plot for antenna 1 and one plot for antenna 2. I've listed out here the channel numbers. Just one thing to be aware of with the DJI system is that channel 8 is between channel 5 and channel 6 for some reason. When we're looking at the nominal output power of the Air Unit, we can see that it is nowhere near the specified nominal output power level. So for 25 milliwatts, we can see that we get about 10 milliwatts out of each antenna. In the 200 milliwatt mode, we're getting maybe 50 milliwatts out of each antenna. And in the 500 milliwatt mode, we are somewhere between 100 and 200 milliwatts out of each antenna, depending on what channel we select and what antenna we're measuring. Even when we get all the way up to 1200 milliwatts of output power, you can see that we're only getting between maybe about 200 milliwatts of output power on average across all the channels and both antennas. And that's way, way less than the 1200 milliwatts that's specified. So how is DJI able to call their top power mode 1200 milliwatts? Well, they're playing a little bit fast and loose with the maths in order to achieve the largest possible number. The first thing they're doing is they are linearly adding together the power outputs of the two antennas. And that's not really fair because having two antennas each broadcasting at 100 milliwatts is not equivalent to having a single antenna broadcasting at 200 milliwatts in terms of range and penetration, because the signals don't always add together linearly. Sometimes they'll destructively interfere, and sometimes, depending on the modulation scheme, you'll be transmitting one signal through one antenna and a different signal through the second antenna, and they're not going to add at all. The second thing they're doing is they're including the antenna gain of the stock antennas that come with the system. And those stock antennas have 4.6 dBi of antenna gain, which is over 2 times. And so that allows them to multiply up their power value to get to that 1200 milliwatts. And that's not really fair either, because as we've said, antennas with high gain don't create energy, they just concentrate it in a narrower beam. So if you've got the two antennas at 4.6 dBi of gain, they are going to have certain areas where they transmit less powerfully and certain areas where they concentrate the power. And if you angle them in different directions, which you should, you're never going to get the full effect of that gain in any one particular direction. It's going to be more evenly spread out. Although this method that DJI use gives the largest possible value, it's not comparable to an analog system, even broadcasting at 1000 milliwatts. Because you could also put an antenna with 3 dB of gain on that analog system and get a system that DJI would call a 2-watt system. So that's just something to be aware of. DJI's way of measuring output power gives a much larger number than the way that we normally measure output power in FPV. Let's take a look at the Caddx Vista now. And this is the Vista running the 606 firmware that's compatible with the V1 DJI system. What we can see is that the power output from the Caddx Vista is very similar to the power output from one of the antennas on the original DJI FPV Air Unit. The main difference with having one antenna versus two antenna outputs is that the antenna on the Vista is going to need to be a slightly lower gain, so it's more omnidirectional. Because with the original Air Unit, you could have two relatively high gain antennas pointed in different directions, and the overlap of the radiation patterns would give you good coverage. You can't do that with a single output, so you need to use a lower gain antenna. And so that's going to be the main difference in range and penetration between the two systems. It's going to mainly be antenna gain, not output power related. The same as with the original Air Unit, the nominal power setting is very different from the conducted output power that we see on the VTX, but we see anywhere from 10 milliwatts up to maybe 400 milliwatts maximum output from the Vista, depending on the channel and power setting. Let's move on to talk about the walk snail avatar system, starting with the V1 VTX. As we might expect, the power output across all the different power settings and channels is very similar, very comparable to the original DJI FPV Air Unit. And we also see that on my Avatar VTX V1, there is a slight decrease in output power with frequency. And so if that's true across all walk snail Avatar V1 VTXs, there might be a recommendation there to run a lower channel number if in doubt, just to get that maximum output power. Now, you don't need an RF power meter to find out which channel has the maximum output power for your VTX. You just need to measure the power consumption of the VTX with a multimeter or using a benchtop power supply. And the channel that has the maximum power consumption is probably also going to have the maximum output power and therefore give you the best range and penetration. Moving on to look at the walk snail Avatar V2 and 1S LITE VTX, we can see that walk snail have changed how they talk about their power settings. Now the power setting in the VTX is much more closely linked to the conducted output power that's actually being transmitted by the VTX. We can see that the 25 milliwatt setting is approximately 25 milliwatts of output power. The 200 milliwatt setting is approximately 200 milliwatts of output power. And the 500 milliwatt setting is not quite 500 milliwatts of output power, but it is the maximum that the VTX is able to provide. The upshot of changing this naming convention is that the 700, 1000 and 1200 milliwatt power settings now don't do anything because the VTX is already maxed out on that 500 milliwatt setting. But you're not getting any less power than you were before. It's just that walk snail is moving away from the DJI naming convention for power settings towards the naming convention that's used on analog VTXs. Let's take a look now at the HDZero VTXs. And the HDZero VTXs showed a lot more variability in conducted output power with frequency than the other VTXs that I tested. Both the HDZero Race V1 and Whoop Lite showed much higher output power on the lower channels than the higher channels, with the difference being hundreds of milliwatts in some cases. I was able to verify this not just by looking at the power output measured by my meter, but also looking at the power that the VTX consumed from the benchtop power supply. Both VTXs were consuming significantly more power from the power supply on those lower channels compared to the higher channels. So if you're looking for maximum range and penetration and you're flying alone, it's definitely worth setting HDZero VTXs to lower channels to try and get the maximum amount of output power out of the VTX. In terms of the accuracy of the output power setting, both the HDZero Race V1 and the Whoop Lite VTX delivered significantly more than 25 milliwatts on that 25 milliwatt power setting. The Race V1 delivering 200 milliwatts on Race 1 when set to 25 milliwatts. And then when switching up to the 200 milliwatt mode, again, the Race V1 delivering a lot more than 200 milliwatts, more like 600 milliwatts on Race 1, dropping down to just below 200 milliwatts on Race 8. The Whoop Lite VTX performed a bit differently. Its 200 milliwatt setting was more accurate, with the VTX delivering anywhere between 100 and 200 milliwatts in that 200 milliwatt mode, with the 25 milliwatt setting again being 25 milliwatts on Race 8, but increasing up to more like 80 milliwatts on Race 1. Let's take a look at the DJI O3 system now. And O3 is interesting because it doesn't have any power settings, so the only way to know how much power it's outputting is by measuring it on the bench. The DJI O3 system has 3 power modes, a low power standby state, an active state, so that's with low power disabled, and an armed state when you're actually flying. And I didn't measure the low power state because the bit rate and the frame rate are very low in that mode, and you should never be using it when you're actually using the system. So we have here the active state and the armed state. In the active state, the O3 system will only transmit on one of its antennas at a time. And my O3 Air unit really preferred to transmit on antenna 2, and it would generally mostly transmit on antenna 2, only very occasionally switching to transmit on antenna 1, and it would never transmit on both antennas at the same time in the active mode. When I switched to the armed state and gave the O3 Air unit a valid armed signal from the quad, it switched into a high power mode where both antennas transmitted at full power. And we see anywhere from 100 to about 200 milliwatts of output power on both antennas, with a small variation in output power with channel. Again, lower channels tended to give slightly higher output power in my testing. And that corresponded to a slightly higher power draw from the O3 Air unit when set to those lower channels. It's interesting to note that whether the O3 system is in FCC or CE mode, the power output from the VTX seems to be identical. There doesn't seem to be any difference in output power between CE mode and FCC mode. The only difference is in the available channels, with CE mode having a narrower selection of channels. The output power of the O3 system when it's armed is most comparable to the 700 milliwatt power setting in the original DJI FPV Air Unit. The final system I want to talk about is the Caddx Vista running the new O3 firmware. And the results of this were really interesting because the O3 firmware has significantly lower output power than the V1 firmware on the Vista. And the only reason that I can think that DJI might do this is because they're worried that if they used the full 1200 milliwatt output power for the Vista, that you would see significantly better range and penetration with the Vista running the O3 firmware than what the O3 Air unit is able to achieve. We can see that the O3 Air unit is anywhere from 100 to 200 milliwatts output power when it's armed, and that the Vista is similar, anywhere between 100 and 200 milliwatts. But we know that the Vista can actually go a lot higher than that. With the V1 firmware, the Vista can deliver significantly more power, 300 to as much as 400 milliwatts, and that would give it a significant range and penetration advantage over the 200 milliwatts being delivered by the DJI O3 system. We'll have to wait and see if there's an unlock or a hack which allows us to use the full power of that Vista 1200 milliwatt mode on the new O3 firmware. I hope you enjoyed these test results and learned a load about how all these different VTXs deliver their output power. If you've watched this far, you must really enjoy all of the independent test work that I'm doing and want to support more of it. I'm currently raising money for battery test equipment that will allow me to test the performance of FPV batteries from tiny whoops all the way up to 5 and even 7-inch quads, so that you can know which batteries provide the best possible performance and which the best value for money. This test equipment is expensive, and so I can't buy it without your support. I'm asking everyone to head on over to my Patreon and join from just a few dollars a month to help support the purchase of this battery test equipment and the batteries for testing, so that we can find out which FPV battery manufacturers are the best and which you should avoid. Currently, after raising for around a month, we are over halfway to the target to be able to buy all of this battery test equipment and get started on the testing. So if you can spare just a few dollars, head on over to my Patreon, and not only will you support the purchase of this battery test equipment, but you'll also get access to special areas of my Discord server, access to all the detailed test results for all the testing that I've done so far, and also information and sneak peeks on new products that are going to be coming out before anyone else. You can find a link to my Patreon in a card on the screen now, down in the video description, or you can just search Chris Rosser FPV Patreon. Thank you so much for your support. Thank you for helping with this battery testing, and I can't wait to see you in the next video. Happy flying.